Well, thank you. My name is Alma. I'm a postdoc at the Santa Cruz Institute for Particle Physics. And I will talk to you about the effect of intermediate massive black holes on the gamma ray constraints on dark matter annihilation from local dwarf spheroidal galaxies. And this is a work that I'm doing with Stefano Profumo and Farin Alakios. So why will we think dwarf spheroidal galaxies host intermediate massive black holes? Well, we have a lot of evidence of massive black holes at very different scales being hosted by galaxies of all different kinds with big bulges, bulgeless galaxies. These galaxies, and all of them from a range from 10 to the 6 to 10 to the 11 solar masses. And we also know of stellar black holes and black holes in globular clusters. So it seems that there can be something in between. Those are the intermediate massive black holes that I would refer to between 10 to the 2 solar masses to 10 to the 5. And for some time, there was a lack of evidence of intermediate massive black holes. But very recently, there was a sample of 150 galaxies with optical evidence of black holes in the range of 10 to the 5 to 10 to the 6 solar masses. So now it seems that the only galaxies that are not hosting black holes are dwarf spheroidals, and that would be the case, or maybe we have just not detected them. And well, there is also some hints of these black holes in dwarf spheroidals, very questionable, of course, but there are some, in particular for the case of Fornax and Ursa Minor. In the case of Fornax, there is an upper limit of a black hole of 1.2 10 to the 5th solar masses, 10 to the 4th solar masses. And for Ursa Minor, it's about the same, 2 to 3 of 10 to the 4th solar masses. And recent searches with the XMM Newton and Chandra are finding some X-ray sources that are coincident with these two dwarf spheroidals. In the case of Fornax, they cannot give mass of the black hole because the center of gravity is not well constrained. It seems to be a lot of asymmetry on the stellar surface distribution, and so they cannot give. They can only give a limit on the accretion efficiency of Fornax that seems to be very low compared to the Eddington limit. And for the case of Ursa Minor, they can give a minimum mass of the black hole, and it is in the range of 10 to the 4 solar masses to 10 to the 5. So it is very questionable evidence of intermediate mass black holes in dwarf spheroidals, but then we think it is worth to see what this is going to do for the gamma ray limits on dark matter annihilation. So the gamma ray flux expected from dark matter annihilation comes from two factors. One, from the particle physics, that basically depends on the cross-section, on the annihilation cross-section and the mass of the dark matter particle, and also the spectrum of photons in which these particles are being annihilated. That can be fermion bosons or photon. And also the other factor is comes from the astrophysics side, and it it is the line of sight of the density of dark matter. So it usually those two factors are very well separated, and one can care about their uncertainties separately. However, when there is a black hole present, we're going to see that this astrophysical factor will have a small dependence on the cross-section and the mass of the particle. So let me review first what the Fermi constraints are now, and then I will give you the constraints with the black holes. So for the Fermi analysis, of course, given this astrophysical factor, it is important what is the density profile on these dwarf galaxies. And as we have been hearing along the morning, it can be core or cusp, and now we cannot say precisely which one of it is. But for the Fermi analysis, they accounted for this uncertainty by considering two different profiles, the NFW and the Burckhardt. And the parameters of each of these profiles are consistent with the velocity dispersion of each one of the dwarf spheroidals. And they do a multi-level Bayesian model for these profiles in order to account for the uncertainties on the priors on these parameters, and also for the distance to the dwarfs. And every parameter that needs to have a prior, they are also constraining it by this technique. So they, at the end, they find a very well posterior distribution of astrophysical factors that does not depend very much on whether you assume an NFW or a Burckhardt. And with this technique, they do a joint analysis for 15 of the dwarf spheroidal galaxies, where they set the particle physics factor, it is common to all of them, and the astrophysical factor was set by this other technique. And they find that their constraints are not very dependent on the density profile as long as it is, as long as the slope is lower than 1.2. And so what we are seeing here is, because in the Fermi data, they have not detected any source of gamma rays that is coincident with the dwarf spheroidals, then we can put limits on the cross-section as a function of the mass of the particle. And those are the current constraints, the solid black lines. And for the different channels of the final states of the particles, and in most of the cases, we are very close to prove the annihilation cross-section that gives the correct relic density. And the error bar, the error bands comes from the Bayesian analysis that they performed to take all the uncertainties into account. So now, what will be the effect of the black hole? If these intermediate black holes grow adiabatically in the center of the dwarf spheroidals, then that will lead to a formation of a dark matter spike due to adiabatic contraction. These ideas have been worked for a long time, and it is known that the final slope after the adiabatic contraction would be of this form. In the particular case of starting from an NFW density profile, the final slope will be 7/3. And notice that these spikes starts approximately at a parsec. So it does not affect the compatibility with the velocity dispersions or so. And of course, there are many factors that can erase or at least smooth this dark matter spike that comes from the scatter of the dark matter by stars and the formation of the black hole off-center or the major mergers of these dwarf spheroidals. The first one is, we think, is not very relevant for these dwarf spheroidals due to the low content of the stars and gas, but the other two can be. So now the astrophysical factor will be calculated by integrating this density profile, but this one is truncated to a maximum scale that is set by the annihilation of the cross-section of the dark matter and the mass of the particle. This is basically set by the evolution of the density of the dark matter particles. And so to now calculate what will be the constraints on dark matter annihilation, we have to assign mass of the black hole to each of the dwarfs. And to do so, we have used three of the known relations for the mass of the black hole with the luminosity, or the mass of the black hole with the velocity dispersion. And we use those three because they are enclosing a wide range of masses for the black holes that are appropriate for these dwarf spheroidals. And so this is how our new constraints looks like, and those are using the original Fermi constraints as a base, because we have to satisfy the same condition. Now we have this implicit equation for the cross-section, for the annihilating cross-section in presence of black hole that we solve iteratively. So we can see that now this is constraints for each individual of the galaxies, and there are many of the galaxies that, if they are hosting a black hole, can exclude already the region of the relic that gives the appropriate relic density. This panel is when I assume the mass sigma, the three-main relation, and here it is the Magorian relation. So, we can see that those two galaxies that do have some hints of black holes on it are given very strong constraints, and actually they interchange between them when we change the recipe for the mass. But in any case, both of them will be putting very strong constraints on the dark matter annihilation. We did the same thing for the Burkert profile, and in this case, the constraints are also stronger, but not as much as with the NFW. That was expected, of course. So, in general, we can be much more constraining than without the black hole, of course, but it highly depends on how do you assign the mass to each of the dwarf spheroidals. So we try to combine all the galaxies as the Fermi collaboration did, and this is what we find for the different recipes of the mass of the black hole. And what it is interesting is that we only need a mass of 100 solar masses or 50 in the case of a Burkert profile, or a mass of 50 solar masses for the NFW profile to be outside of the current Fermi constraints. So even if this recipe that we put is unrealistic because we are not taking into account the effect of from the black hole off-center or the interaction with the stars, it is possible that the presence of the black holes, at least in Fornax and Ursa Minor, can give more strong constraints than Fermi collaboration is currently considering. And we do also the same for other annihilation channels. What I presented was for the bottom quarks in the final state, and this is for W bosons and taus. And also will be very constrained by the same means. Thank you.
Thank you. This is Westcliff Drive.
Yeah, that's right.
My favorite place.
It is my favorite place, and.
But you're not living there, isn't it?
No, that's why it is my favorite. Yes.
So thank you very much. We have maybe time for one or two questions.
It could actually be worth that not only you know how steep the cusp is. I think in principle it could go the other way. I think the only galaxies that really know that they're black holes are massive ellipticals. We actually think that on the collisional stars it has the opposite effect, because we think they are binaries that actually scatter out the collisionless particles. So we think that in the ellipticals we actually produce a large core by having a black hole in it, because occasionally you will have a binary that actually kicks out all the stars. So it could actually go the other way, that instead of having a cusp, we actually have less dark matter, if we have more than one black hole.
Yeah, but in these dwarf spheroidals, we don't have so much stars, I guess.
So, thank you very much.
Minor, it's about the same, 2 to 3 of 10 to the 4th solar masses. And recent searches with the XMM Newton and Chandra are finding some X-ray sources that are coincident with these two dwarf spheroidals. In the case of Fornax, they cannot give mass of the black hole because the center of gravity is not well constrained. It seems to be a lot of asymmetry on the cells, and that would be the case, or maybe we have just not detected them. And well, there is also some hints of these black holes in dwarf spheroidals, very questionable, of course, but there are some, in particular for the case of Fornax and Ursa Minor. In the case of Fornax, there is an upper limit of a black hole of 1.2 10 to the 5th solar masses, 10 to the 4th solar masses, and for Ursa Minor, between 10 to the 2 solar masses to 10 to the 5. And for some time, there was a lack of evidence of intermediate massive black holes, but very recently there was a sample of 150 galaxies with optical evidence of black holes in the range of 10 to the 5 to 10 to the 6 solar masses. So now it seems that the only galaxies that are not hosting black holes are dwarf spheroidal massive black holes at very different scales, being hosted by galaxies of all different kinds with big bulges, bulgeless galaxies. These galaxies, and all of them from a range from 10 to the 6 to 10 to the 11 solar masses. And we also know of stellar black holes and black holes in globular clusters. So it seems that there can be something in between. Those are the intermediate massive black holes that I will refer to. Well, thank you. My name is Alma. I'm a postdoc at the Santa Cruz Institute for Particle Physics. And I will talk to you about the effect of intermediate massive black holes on the gamma ray constraints on dark matter annihilation from local dwarf spheroidal galaxies. And this is a work that I'm doing with Stefano Profumo and Farin Alakios. So why will we think dwarf spheroidal galaxies host intermediate massive black holes? Well, we have a lot of evidence of